Thank you, Zhen. Hello, everyone. Today, I hope I can draw your attention to the impact of three important factors: the parameter selection, amount of data, and task condition on the test-retest reliability of dynamic network measures developed from the network neuroscience field. So, building on the graph theory, network neuroscience summarizes neuroimaging into a graphic representation by treating the brain regions or parcellations as nodes and their functional interactions as edges. So to build a graph, once we have this graph, and then numerous network metrics can be applied to quantitatively describe the architecture of this graph. So when we study the brain networks, an important concept is the modular structure. So these densely connected modules usually serve as specialized functions, such as visual, auditory, or higher order attention functions. With the development of the network neuroscience, the theoretical frameworks and mathematical tool sets allow us to map the modular organization of the human brain more comprehensively and in greater details. One of the emerging frontiers of network neuroscience is the investigation of the network dynamics. The research in this area explodes after the development of the multi-layer network community detection algorithms. The beauty of this algorithm is it introduces a temporal dependency between different layers, so allow us to model the dynamic changes in the modular structure over time. So here I will introduce three key measures of network dynamics. They are recruitment, integration, and flexibility. So recruitment, to simplify, it quantifies the functional interaction within a module, for example, the visual system, like how much interactions happens over time for this given module. And integration quantifies the functional interaction with the module, between modules. So for example, between visual system and the rest of the brain. And flexibility is the frequency a region change its community structure. It quantifies the allegiance of a region to its own community. So now here I will briefly explain how these measures are computed. Once we extract a time series from the nodes, we apply a sliding window. It can be overlapped or non-overlapped. Well, it's an open question which way is better. And the same thing for the edge estimation. There are different metrics there. It always depends on the question at hand, and it has pros and cons for each way. So, and then once we have the window, the function connectivity, we link them into a multi-layer network by connect a node to itself in the time windows preceded and following it. And then apply a multi-layer community detection algorithm. So a popular way to study community structure is to optimize the functional parcellation by maximize the difference between the total weights of the observed network and the null network. So it's called the quality function. So by operating on maximizing this quality function, we can find the optimal partition in a network. And in this equation, you can see there are two parameters are essential. One is called gamma. It's the intra-slice coupling parameter or structural parameter. So it controls how much weight we give to the null network. So if gamma is 0, and then all the nodes are assigned to the same community, and if the gamma value increases, and then we assign more weights to the null model, which means the nodes are harder to be glued together as a community. As a result, we have more numbers of community. The other parameter is omega. It's the inter-slice coupling parameter. It determines how strongly the different time windows are connected. So if its omega is 0, and then all these time windows, they're independent, and the communities detected in one window will be unique differently from the other windows. And when we increase the omega value, and then we introduce some dependency, which means the community detected in one window depends on the community detected in the other windows. So after applying this multi-layer community detection algorithm, we obtained some community assignments within each window for a given node. And this can be summarized into a vector for each window. So the flexibility that we can use to compute flexibility. Flexibility is simple. So across all these time windows, for example, if I have 11 windows, now I count how many times a node change community membership across like all 10 possible changes. Once you have 11 windows, you have 10 possible changes. So if the node change community membership 5 times, then your flexibility is 0.5. So for recruitment and integration, we need to sort that vector into an adjacent matrix. It's n by n. N is the number of nodes. So a value of 1 in that adjacent matrix will indicate 2 nodes are assigned to the same community. And if it's 0, and then those 2 nodes are assigned to a different community. And then we average across all the windows to get that modular allegiance matrix, which quantify how consistent a node is assigned to the same community with the other nodes. Okay, so the initial application of these methods to neuroimaging data have provided novel insights into how these network dynamics contribute to the learning process. Specifically, using a simple motor learning task, Dr. Danny Bassett has demonstrated the flexibility in one session can predict the learning rates in the following session. And also the practice-induced modulation in recruitment can also predict the learning rate in a different session. So following this initial demonstration of potential utility, there is a growing range of application of these methods to study of inter-individual and group differences in cognition and disease. And here we can see probably, oh, okay, it's pretty good, yeah. Sorry, it's small. So we can see these studies using different tasks and with different scan duration. For edge estimation, usually people either use wavelet coherence or Pearson's correlation. For gamma and omega, these 2 parameters, it's relatively consistent around 1.1, which is commonly used and recommended value. The flexibility range is relatively small, lower than 0.25. So although these results are intriguing, and the problem is the test-retest reliability has not been systematically assessed. Also note, there is a change in the Zhen function, which is a multi-layer community detection algorithm. It's the core of all these analyses. So in 2014, the developer observed there are some undesirable behavior when applying this algorithm initially adapted from the static community detection. So that default move will result in some undesirable and abrupt changes when applying to this multi-slice community detection settings. I don't have time to go through like the details of what these options do. If you're interested in, you can read this Bazzi et al. 2016 paper. So they first demonstrate these changes in financial data. What is important is here we also observed a similar abrupt change in our neuroimaging data, which is shown in health-brain network data, replicated in the Human Connectome project, and further confirmed in a toy simulated data set. So the problem is, if you use original move, and if your parameter selection gamma and omega is 1, 1, the temporal dynamic measures you computed could be inaccurate. So for these considerations, all our analysis, we used this new option, move rand W, which controls how a node is moved to merge as a community. So the goal of our study is to optimize multi-layer network derived measures, so we can apply them to to study individual differences. So I will talk more later about the specific goals. And the data set used is a Hellsbury network, serial scanning data, 10 subjects. Each subject have 12 repeated function scans. Each session has 3 tasks, rest, inscapes, and moving. Each task is 10 minutes. So I already explained how those measures are computed. Specific here is we use the CREDOC 200 function postulation and use U7 networks to compute integration and recruitment. So for our goals, the first goal is to identify the optimal range of gamma and omega that can give us the high test-retest reliability. And we quantified the test-retest reliability using intra-class correlation coefficient. And we use the maximum amount of data we have. So we split the 12 sessions into dataset 1 and dataset 2. We focus on the moving condition. Once we have the optimal parameter, we apply to rest and inscaped to determine how the task condition impact the test-retest reliability, and further conformed using a hierarchical linear mixed effect model. And lastly is we want to evaluate the scan length on the test-retest reliability. So we find the test-retest reliability depends on the gamma and omega selection. Here we can see in some area you have low test-retest reliability, and some area you have high, which are surrounded by the red line. And to understand what contributed to this high and low test-retest reliability, we looked at the mean and between subjects variation. So we find that these features are also vary, depends on gamma and omega selection. So the high ICC values are overlapped with low magnitude of the dynamic features, and also with relatively high between subject variation. And here we choose the parameter gamma equals 1.05, omega equals to 2.5 with optimal ICC values, and then compared with the commonly used 1.1. And we find, yeah, the spatial topography is similar in these two parameter choices. However, the between subject variance is much lower for the gamma 1, omega 1, so which may partially explain the low ICC obtained with these parameters. And then next, we apply this parameter to rest and inscapes, and we find across all these conditions we have high test-retest reliability, although for the moving condition we have relatively higher test-retest reliability. And this is confirmed by the hierarchical linear mixed effect modeling, which support the idea that if we are short for one type of scan task condition, we can combine different task conditions to improve the amount of data as a result of and improve the test-retest reliability. So lastly, we looked at how the scan length improve with the increased amount of data. And here, what do we find? If you only have 10 minutes of data, across all these 3 measures, the test-retest reliability is low, and you can see it's all blue here. And then once you increase your amount of data to 20 minutes, and then we can obtain some medium-sized reliability. So once you're up to 60 minutes, your test-retest reliability is good, except for visual cortex is still the medium-sized. So what is the take-home message? The take-home message is, first, the Jean-Laurent code matters. So if you ever apply these methods, we recommend to use move rand W. And also the gamma omega matters. Here, because our interest is inter-individual differences, so we recommend maybe we can use the test-retest reliability to guide your gamma and omega selection. And thirdly is the data length matters. A minimum of 20 minutes of data is required to obtain a medium test-retest reliability. If you want a high test-retest reliability, more data is needed. And fourthly, scan condition may matter less. So our results support combining across different scan conditions to improve the test-retest reliability. Our study can answer a few questions. Actually, it opens more questions. So for future work, it's important to evaluate the impact of scan parameters, pre-processing steps, and multi-layer network analysis related other important methodological decisions on reliability. And the natural extension of this work is now that we established a high test-retest reliability, we can apply these measures to study the individual differences, such as like depressive or anxiety symptoms. I would like to thank my colleagues and collaborators. It's a team effort. Thank you very much for your